What's up, guys? Our next lesson is over arcs and sectors of circles. Pretty easy stuff, so we'll get right to it. Our objectives today are to find arc length, which is basically just part of circumference of a circle, and area of a sector, which is just part of an area of a circle. Um, our curriculum teaches the chapter over circles before area, and I've chosen to reverse that. And so there are a few vocabulary things we need to get covered. Um, and we'll do that pretty quickly. You can go back and rewind this as many times as you want to get this down. All right, everybody knows what a circle is. A circle is defined as all the points in a plane the same distance away from another point called the center. And so this would obviously be circle U, and a circle would be all of this green stuff. It's not like you didn't know that, but I just wanted to tell you what the definition was. So a circle is more like a ring than it is like a disc. All right, so just remember that when you're thinking about circles. Central angles are simply angles whose vertex is the center of a circle. There are three kinds of arcs. Minor arcs are less than half of a circle. Major arcs are more than half of a circle. And you guessed it, semicircles are exactly half of a circle. This idea is very close to acute, obtuse, and right angles. You just kind of substitute the number 180 instead. And we'll talk more about this in just a second, but arcs have measures, which are numbers of degrees, and they also have lengths, like a segment. But as far as their measures go, if it's less than 180, we call it minor. If it's more than 180, we call it major. And if it's exactly 180, we call it a semicircle. A sector is like a slice of pie or slice of pizza. All of that shaded in, and we're going to find the area of those in just a minute. And then chords are segments whose endpoints are on a circle. Diameters are special chords that go through the center of a circle, like this one. There's another one, segment TR would also be called a chord. All right, now as far as the problems at the bottom here where we find the measures of arcs, the first thing that I suggest you do is you find the measure of all the central angles. Two of them, of course, are given, and using some old concepts, easy stuff, we can figure out that one's 42 because of vertical angles. This one's 74 because we can assume lines are straight, and these have to add up to 180. Lots of reasons you can figure out this one over here is 138. And of course, we're talking about circles, so one thing I would always do to double check it, go all the way around and make sure they add up to 360. All right, and then as far as finding the measure of arcs, a couple quick things here. Notice, just like with angles, there's a little lowercase m out in front of it. Sometimes arcs are named with 2 letters, like these two. Sometimes they're named with 3. We'll talk about that difference in just a second. And then instead of a straight line above it, there, of course, is this little curvy arc above it. So that's how you're going to write these down. And the measure of an arc is simply the same as the measure of the central angle that creates it. It's that easy. So when an arc is named with 2 letters, like arc TS, you always take the shortest path between them. Another way of thinking about that, arcs named with 2 letters are always minor arcs. So the measure of arc TS, which is right here, is just the same as the central angle that creates it, 74. Second one, arc PS, again with 2 letters, you always take the shortest path. So you simply add these 2 up, and you'll get 138. And then if an arc is named with 3 letters, the first and last one are the endpoints, but that middle letter kind of gives you direction. So instead of going from T to S the short way, the name of this arc is TPS, and you must start at T, go through P, and keep going until you get to S. So it's almost all the circle. Matter of fact, it's everything except 74. So you could do 360 minus 74, or you could add all of these up. Either way, you'll get 286. And then finally, measure of arc PQR. There's P, there's Q, there's R. You can see that's exactly half a circle, so that's going to be 180 degrees. And again, just a review from earlier, this would be minor, this would be minor, this one's major, and this one is a semicircle. All right, now that we got the new vocabulary out of the way, we're going to talk about finding arc length, which is just a portion of circumference. And like I said a minute ago, arcs also have a measure, which is a number of degrees. So be real careful you know which kind of measurement they're wanting you to find. And this proportion is all you need. All right, the measure of an arc is always a number of degrees. This part's always 360. Put your length of the arc here. And I wrote the word circumference. Sometimes you may leave it just as a capital C for circumference. Sometimes you might want to think of it as pi times d or 2 pi r, or however you prefer to think of the circumference formula. But you'll plug in everything you know and then just simply cross multiply and solve for what you don't. All right, so here's our first example. We have circle Q. By the way, I think I forgot to mention it earlier. Circles are named by their centers. And if a point is ever in the middle of a circle and it's not real clear, you can go ahead and assume that it's the center. And I think I forgot to type it on this example, but this is definitely circle Q. So let's find the measure of arc AB. That is the distance from there to there, which is simply part of circumference. All right, the measure of the arc, of course, would be 120. The length of the arc is our variable. The bottom left part of your proportion is always 360. And then, like I said, I just thought of the formula for circumference, 2 times pi times r. R, of course, is 6. And this is pretty easy math, so I'm just going to uncover it and let you look at it. Obviously, your variable there is capital L. Just cross multiply until you get your answer, and it does say round to the nearest hundredth. By the way, if it did say exact answers, when you're dealing with circles, that just means leave pi in your answer. So the exact answer is 4 pi. The rounded answer, of course, is about 12.57. All right, next one's pretty similar. Let's find the length of arc AB. So top left of your proportion is 45. The bottom left is always 360. There's your variable again, and this time the radius is 12. Pretty much the same story as the last example. Exact answer would be 3 pi, but the rounded one is about 9.42. All right, why don't you pause the video for a quick second or two, see if you can figure this one out before I uncover it. And we'll have 90 on the top left, 360 on the bottom left. Your variable is L, and it's 2 times pi times 7. There you go, about 11. Now keep in mind, this is still a rounded answer. It just happens to be 2 zeros to the right of the decimal. And again, I know it says round to the nearest hundredth up here, but if this said exact answer, 7 pi over 2 is a much better way of writing it than 3.5 pi. In other words, don't mix decimals with exact answers when you're using pi. Convert them to fractions instead. All right, sector, as we defined earlier, is kind of like a slice of pizza. It could also be kind of thought of as this Pac-Man shape, but it basically boils down to being part of the area of the circle. Now, this is kind of a fancy way to define it, but like you saw earlier, I shaded in a sector in green. And these two radii of this circle are dividing this one into 2 different sectors. And the way we find the area of those sectors is real similar to what we just did. Matter of fact, the left half of your proportion is exactly the same, but the right half, instead of being length, is now area. So area of sector goes up here, and area of a circle, which y'all know is pi r squared, will go down here on the bottom right. Okay, when you're doing these examples, if you ever see a measurement on the outside of a circle like this 60 degrees, you need to assume that it's always referring to the part of the circle that it's nearest. In other words, what this is telling you is that the measure of this arc is 60 degrees. And from what I told you a few minutes ago, that means the measure of this central angle is also 60 degrees. They just happen to put it in a different place. So when you see that out here, just always assume it goes with what it's nearest. All right, so there's our proportion. We'll have 60 over 360, and I just used a big capital A for area of a sector. And since our radius is 10, there's how we find the area of that circle. There's all the work. So again, at least to the nearest hundredth, it's about 52.36. All right, next one. This time the measure of your arc in question would be 90. Radius is 6. So that's how it would look when you set it up. And your final answer is about 28.27. All right. I'm going to give you one hint, then I want you to pause the video and try this one. This is just simply saying, and it's kind of a different way than we usually mark it, that all three of these angles are congruent. And you'll kind of need to know that to figure out the area of this shaded sector. So pause the video, give this one a shot, and see what you get. All right, 1/3 of the circle, of course, is 120. Your radius is 24, so that's what it should look like when you set it up. And you get about 603.19. All right, so that's pretty much it. These next few examples, I've kind of changed a slight thing or two about it. You just have to kind of read it carefully and make sure you know what it's asking about. So the length of segment AB, remember, only 2 letters, is the shortest path. This is what we want. And so we'll put 135 over 360. Now I'm back to arc length and the formula for circumference. Don't get those mixed up. 23.56. All right, number 8's a little different because I'm asking for the circumference of the circle, and this time I know the arc length. So like I said earlier, anytime there's a measurement out here on the outside of a circle, excuse me, just assume it's referring to the thing that it's nearest. So that 15 inches is referring to the length of arc AB. Just a reminder, the measure of arc AB would be 60 degrees, but the length of it is 15 inches. So this time your proportion would look like that, where your variable is down here. Now the reason I just put a capital C is because all we want is the circumference. There's no reason to put the formula. Just stop right there and do the simple algebra, and there you go. The circumference of that one is 90. All right, this time again we have an arc length. We have an exact arc length, as a matter of fact, because it has a pi in the answer. We know the measure of the arc is 90, and we want to go to the radius. So when you set up this one, instead of putting a big capital C down here, I'm going to put the formula for circumference because R is my variable. All right, now I will uncover this one step at a time, because when you cross multiply, when you cross multiply here, you'll get 180 times pi times R, and this one will give you 6,480 pi. I did include on the work shown here dividing by 180 pi just to show you that the pi's will cancel, and I'm going to assume you can use your calculator correctly from there. You'll get 36. Just a word of warning, if you wanted to type that in your calculator, remember to put this in its own set of parentheses or figure it separately or something. And I've shown you all that in, more than once, so just be careful you know how your calculator works. All right, next one. We have a capital A, which stands for area, about 20.89, and like I said, that's referring to this gray shaded sector. We need the radius of this circle, and so this time, that's what it'll look like when we set it up. Now, where does this 282 come from? Well, you got to be careful, because if I know this area is about 20.89, that's the central angle I need to use. Technically, it's really the measure of this arc, and that's why it's greater than 180. So 360 minus 78 is where I'm getting 282. And since the ultimate answer is the radius of the circle, I replaced the area of a circle with the whole formula. Do all the math. About 2.91. All right. Why don't you pause the video one more time, see if you can figure out the area of circle S, and then check and see if you get what I did. All right, so there's your original proportion. Pretty simple. Should get about 81.30. All right, one more time, pause it to see if you can figure out the area of circle S. So there's your proportion. Just cross multiply and solve for A. Nothing to it. All right, these last few examples are kind of the challenge problems. This type of picture in particular, I wanted to be sure I put in the video because there are some questions like this on your assignment. We talked about chords earlier, so segment ED would be a chord. And when you draw a chord of a circle, you divide a circle into two segments. Now, obviously, we've used the word segment all year long, but a segment of a circle would be like this kind of green-gray shaded part, or all of this white part. All right. And the question here would be, how would you find the area of a segment of a circle? And we'll just kind of talk about this green part out here. Well, you just saw a bunch of examples where you could find the area of the entire sector. And obviously we don't want to count this triangle. And so we would simply find the area of that triangle and subtract it. Now, I'm not going to do these in depth for you, but I will give you a little bit of a hint here. Let's assume we know this angle. And remember, if you drop down this segment so that that makes a right angle, you can now call that the height of triangle OED. This distance, of course, sorry about that, would be your base. And so to find the area of just that white triangle, it's 1/2 times this times this. Now, one thing you already know about a circle is that radii are the same no matter where you draw them. So segments OE and OD are congruent, making this white triangle isosceles, and we've talked about that at length all year. My last hint to you is that clearly you have a right triangle here, and so a triangle like this might be one of our special right triangles. You might have to do Pythagorean theorem, maybe basic trig, all that stuff that I've been telling you all semester you're going to do a lot of in order to figure out H and B and ultimately get the area of this entire white triangle. Again, I know I'm not going to show you every detail of it, but that is pretty much how you do it. And then on these next few examples, the answer is already uncovered. So I would strongly encourage you to take some time, grab some scratch paper, and just work it out to make sure you get the same answers I do. All right, so if that's a 120-degree angle and this is 24, the area of this blue part is 353.77. Sometimes the challenge problems kind of disguise a circle split up into two arcs. So like the area, let's start with perimeter first actually. The perimeter of this shaded part would be, I'll give you the 15 plus 15 part, that's pretty easy. And even though one arc is here, a semicircle, and one arc is here, you can just find the circumference of one circle and add it up. Now, when you do all that, you should get 58.27. Area, you can see the answer down there. I guess the best trick would be to show you that the area of the gray part is just the rectangle minus, I'll just put a dot there, this sector, minus this sector. And the last one, area and perimeter of something like this. Again, just with minimal help. If I drew in this part, area would be 3 rectangles, 1 triangle, and 3 sectors. Perimeter would be 4 and 4 and 4 plus this arc plus this arc plus this arc. So again, my suggestion is that you take some time, work all that out, make sure you get these two answers. And as always, if you have questions, just contact me. Good luck with your assignment.